Right, good afternoon, everybody. My name is Supreet Oberoi. And today I'll be talking about providing industrial observations at scale with computer vision. So this is an industry talk, maybe a bit of change of pace from the last few ones. About myself, I was the Vice President of Engineering for the Oracle IoT Applications. I built the analytics components for them. Specifically, the applications such as IoT asset monitoring, which monitored high capital assets. Are they up? Are they down? Where are they? Are they showing any problems? Monitoring machines in a factory in real time. Monitoring, and this was a production monitoring application. Fleet monitoring, where we monitored perishable cargo, such as produce, pharmaceuticals. Connected worker, where we monitored workers for safety in engineering and construction and mining. And then service monitoring, this is for field technicians. These deployments were done in a variety of verticals, such as aerospace and defense, automobiles, finance, retail, engineering and construction, lots of them, government, Industry 4.0, modernizing the factories, and in logistics as well. This also involved using a lot of AI and ML as well, starting from basic things like metrics for total cost of ownerships, KPIs, but then looking at these sensor signals and trying to find anomalous events. By correlating these anomalous events, we try to get into the root cause analysis. When something goes wrong, why did it go wrong? It's a very complex challenge. And from those insights, codify and build the rules so that not only can we monitor them in real time, but can also make predictions based on that learned knowledge. And finally, doing forecasting on how to run the business, how to make the optimal operations. For this, we had to collect signals from a lot of places, from different sensors, from different applications, and Matroid for computer vision. And specifically, what that meant was that for our applications, we started collecting signals from the camera, and we sent those signals to the Matroid application, and they did all the magic with image classification, object detection, object recognition, in some cases object tracking, and returned us neatly classified data on which we can do analysis and apply our existing machine learning algorithms. So with insights from this background, today what I'd like to talk about is that computer vision is one of the most important applications of machine learning in industrial IoT. I will go through some use cases for that. And for computer vision to meaningfully solve these enterprise-class problems, it must provide a path to scale. And there are multiple dimensions to scale. Part of it is the science that we talked yesterday when we had talked by Pitt. It's not just the technology, but also the scale of adoption drives some technical needs as well. And we can get even richer insights by correlating the data. Think about how do we provide overall situational awareness in some respects. And Matroid has been a very important part of our IoT offering, Oracle's IoT offering, to solve such industrial use cases. So the first part is the case for computer vision. Now, while most of us do understand intuitively that put eyes on a computer and the computers will become smarter, but let's go through some salient points where this becomes more important. If you look at the electromagnetic radiation, the span of the wavelengths, they go from a few kilometers for radio waves to wavelengths that are just a fraction of the size of the nucleus. And in this entire range, the wavelength that's visible to the human eye is a very small part of it. And only objects that reflect that small range are the ones that we see with our eye. So what does that mean? In this picture, this is of a chemical refinery. The picture below is one taken by an optical camera. The ones above have been taken by infrared cameras. This is from FLIR. And now all of a sudden, the hydrocarbon gases become visible. And now I can start doing things like detection for leakage. In this example, the picture at the top is, again, an aerial picture taken from an optical camera. And the one below has been taken from a SAR satellite using microwave radiations. Microwave radiations have a larger wavelength. They can percolate clouds, snow, depending on the frequency you use, foliage, even the top layers of the soil. So what you're seeing is an ancient historic construction that is buried just under the surface that you cannot see with the human eye. More commercially, computer vision allows for minimal new capital expenditures and new protocols for observation. It's a mouthful, I'll tell you what that means. This is a use case for doing worker safety. in our industrial IoT space, pre-computer vision, we had to consider making the helmet smart, putting some sensors and devices on it, putting wearables to track the user, having RFID or other indoor positioning systems to enforce geofence monitoring. This is a hazard zone, don't cross it. And even then, we couldn't do a lot of things. For example, one of the most common requirements is that you want to keep a distance between heavy moving objects and workers. It's very tough to do it with traditional devices. If a worker is not wearing one of these smart vests, we cannot track its safety. In addition to that, there's a large cost involved upfront of buying these sensors, connecting them, and then there are the union regulations which view these monitorings as very intrusive. So here is an example where computer vision, deploying the cameras at the right places, you can catch many observations, and it's a lot more acceptable to unions compared to these ones. Here is an example for pipeline monitoring. Pre-computer vision, we put hydrocarbon sensors. There are multiple challenges, including data collection, but over here, I would like to emphasize that the efficacy or the accuracy of the sensor depends on how close it is to the leakage. What you're seeing in this picture is a UAV that's carrying an infrared camera. The UAV flies and walks over the pipelines and detects these leakages in real time. So it's more catch-all, and it's also more efficient. The last point is that a modern computer vision system can observe and comprehend at scale. It's a modern one. We've had machine vision for some time, and they could do things like detect a person. But now we are asking for more things. One is the scale of context. Who is this person? Is this person a VIP customer? Have they made purchases before? Through other channels such as phone, text, chat, what is their sentiment? Are they happy with our brand or not? What can we do right now when the person is there? The other one is making observations on scale of time. And what that means is instead of just this one-off image, I'll be processing a feed to determine a behavior. Is this person standing next to a stall and is reticent about buying a product? Should I send a shopping assistant there? Is this person showing suspicious behavior indicative of theft? And there are other use cases as well. And if you think that all of this computation is very computationally expensive, imagine doing all of that in real time across all the subjects. And that's where the issue of scale starts coming in really hard. So let's go through some real-world examples of computer vision. I anonymized the specific engagements, and we've seen a repetition of that across various examples. So the first one is starting off from the simplest one, and the aim is to give you a feel of how computer vision is being deployed in industrial scenarios and how are the challenges unique. So the first one is it's for an oil and gas company, and they have to transport both oil and gas from the jungles to the port. So there are these pipelines where they have to send the workers to inspect them in areas that are sometimes dangerous to arrive, and they want to monitor that the persons do show up for those inspections. And here's where Matroid really helped us, not only just to do people detection and make sure that the person is showing up, but from Razor's talk from yesterday, the stream monitoring feature was very useful. If you remember, and again, I'm taking a representative example, you can set up a live stream. This is the case of monitoring for cars on Golden Gate Bridge. And whenever it monitors a car, it creates an incident or a report for that in a calendar-like format. That was extremely useful. And the technical need for doing people detection spans multiple use cases. In this particular case, they want to monitor that there's always an attendant on duty. So not only did we want to ensure that there's a person, but with Matroid, we could actually tell that the person is attentive, the person is standing as well. And the second thing was they wanted to track the time to service a customer, and I'll be coming back to that later. Now, from going from object detection, we have started to get to business metrics, and that becomes very vital. Going to a more complex example, this is for a real estate company doing geofence monitoring. They already had a solution that does motion detection, and then it sends an alert to a security guard. Real story, in the alleys, there are lots of cats. And in the night, when the cats start jumping and prowling around, they created a lot of false positives. And with computer vision, it was very easy for us to start discriminating between different classes of objects. And the second one was to gather evidence more efficiently. But before we get there, I mean, some of us, including my old teammates, when we started the journey, we are thinking, well, I could do a lot of that with programming. I would pick up a package like Tensorflow. There are some great tutorials over there. All I have to do is get some training images if I have to do facial recognition, extract the encodings, and then train with the labeled data using FaceNet. And then after that, I captured from the webcam, I captured the frames using OpenCV, use the HOG algorithm to detect the faces, align the face, using face landmarks estimation, extract the encodings using ResNet again, and make a prediction, right? I mean, I have this control. What's wrong with that? Well, there's nothing wrong. It's a lot of lines of code in TensorFlow, which is fine. But this is the industrial scenario, and let me go through 4 key points. First one is that this approach is programmer-centric, which is correct if you're a product development company. When we are deploying it in industrial scenarios, either there's limited programming talent, or more importantly, the person who might be using this may be a different person. It may be a supervisor for a security shift. It may be an MBA that we can talk about. So you have to get to operator-centric. Next one is that even if you're good, getting started with computer vision is easy, but it takes time to catch all the corner cases. Making sure that you're making the right inferences from different angles, from different lighting scenarios, from variations. And you want people who have done that so that out of the box, we start getting high accuracy for these models. Third one is there's a lot of work in public forums about facial detection, but what we'll talk about is it quickly moves from there to detecting non-face characteristics, sometimes non-human characteristics. I'll discuss that. And then from dev prototype, it's not just about scaling it, but I want to be monitoring in real time. I want to be doing historical analysis, for example, for forensic application, and those things need to be supported as well. Going back to the same example, the customer also wanted to do forensic analysis. So when an incident happened, they want to look at, here's an example, suspicious car, for example, and then efficiently traverse all their video archives to see if there's something similar. This is the collections feature that Reza talked about yesterday. Very, very helpful over here too. And here you can see that while we started from human detection, how the use cases very quickly progressed to tracking cars, sunglasses, cups, and other things. So the first takeaway is that a programmatic approach to object detection does not scale in deployment scenarios. That's the important part in real-world cases. An example of a mining company, they have these operations in remote areas. The roads are very dangerous, and the truck drivers carry explosives and gasoline to those sites. So it's important for the company to ensure that the driver is operating safe policies, such as they have the seat belt on, they have their hands on the wheel, they're not eating, taking calls on the cell phone, or taking unauthorized breaks. And here's an example of now we've started to look at things of monitoring whether you have a seat belt on, whether you have a helmet on. Over here, the second detour, what I want to make is talk about the importance of having human in the loop. And one of the best talks that I heard was from Stitch Fix that illustrates the concept. Stitch Fix is an online service that sends you clothes. Behind it, there is an algorithm that curates, that creates a list of clothing that you may like. And then there's a fashion expert who curates that list based on conditions. Well, the person is going on a ski trip. She sent me an email, they're going on a ski trip. Let me put some more clothes for winter clothing, for example. And then that package is sent to the client. The client keeps the clothes that he or she likes and returns the rest. So there are 2 feedbacks in the loop, one from the expert and one from the customer, and that feedback loop helps improve the accuracy. And this is really important in industrial cases because not only does it free the algorithm developer from edge cases, when a machine breaks all signals, the time series looks really warped, and you need to know somebody to say, well, this is when a calling event is going to happen, disregard this data in your training stuff. And it also helps in leveraging the tribal knowledge, the expertise that sits over there. So in our case, one of the features that was extremely useful was the Salience EMAP. Again, as Reza explained yesterday, Salience EMAP highlights the pixels that contributed to the classification. So why is this important? We have models that are out of the box, But when they're deployed in the field, in the different lighting conditions, different orientation, there's a challenge. These models need to be tuned, and understanding how they can be tuned reduces the total cost and risk for that. So that was very helpful. In addition to it, Salience EMAPs helps eliminate biases as well, unintended biases that should be there, and understanding how it happens. Another very important feature for us was the Matroid board. In this example, on the left, on your left too, you see pictures with seat belt. On the right, pictures with seat. And you see that the Matroid algorithm does a very good job classifying these two sets, except for the image that's in the center. It's not too certain. And in situations like that, getting a human in the loop to label the image becomes very important as well. So the next thing I want to share is, to summarize, is use experts wherever possible to improve human accuracy. There's a lot of knowledge and wisdom that sits in people who run these operations, and it's a shame to lose it with automation. Another example, to consistently enforce geofencing for a petroleum company, and to capture, these are industry terms, man down, man hit, man not wearing equipment, they're hurt. So now we are capturing actions, it's not just a person. And having out-of-the-box implementations help reduce it. More interestingly, a rail operator is recording the feed from a camera that's installed in front of it, and they want to look for anomalous things in the rail infrastructure. So that could be obstructions from people in the secure areas, from cars that have been parked too closely, from garbage that's been left right next to it, or foliage that could have grown across it. So again, as you can start seeing, it's not just about the people. You have to collect multiple things from there. And here's a screenshot of how the webcam looks like in this particular area. And over here, I'd like to talk about what does it mean to provide operational visibility or situational awareness. And so far, what we've been talking about is we are monitoring an asset like a train, and we are looking at garbage, or we're looking at the GPS, maybe we're combining it. We are observing raw signals. Where we really want to go is a picture like this, where we are comprehending the overall state of the business. Where are all my trains? How are they performing? How is it impacting my business? And from this overall comprehension, projecting what are the risks to my business? And from those risks, what can I do in a proactive manner to mitigate those risks? So not only is it just about the measurements, but now you start getting into these KPIs, key performance indicators. Which trains are on time, which are getting delayed? What are my top performing lines on which there are never delays? What is the cost impact of the delays that's happening? Doing alerts, like user configurable alerts. Which trains are running later than 30 minutes? Pattern-based, where has there been rain that could be indicative of, for example, a delay in the train, or AI and ML-based. But the most important insight is when you take these raw signals and give a business-level insight. Imagine that the camera looks at a car park and starts saying there's a 25% chance that the shipment from a customer, Acme, will be delayed. That's a value at a different level. So how do you do that? Very easily by doing a big join. So you augment the observations. We know we have a camera. Camera we know is a part of a train that is fulfilling an order for a customer. It's operated by a worker, and it has a history of observations. And based on those history of observations, we know what incidents happened, how much delay it happened. This information sits in different silos. It sits in different applications, back office applications, supply chain applications, customer exchange applications, logistics. When you break down these silos and correlate this information, you start getting these insights that are extremely helpful and valuable. So the takeaway point is that augment computer vision, or in fact, any signals that you're getting with third-party sources, with internal different data sets, and start getting bigger and better insights. In conclusion, the key takeaways, the first one is, as video feeds become more actionable in the enterprises and businesses, you'll see a new class of data assets that have to do with images. In our engagements, we saw pilots starting from a few hundreds of cameras already. And the reason is because these enterprises have IP cameras deployed over the last few years anyways. Start with a few hundred, then we'll go to a few thousand is what we heard again and again. And that was a very sobering moment to understand the scale that happens. Second, in terms of the like many AI-based automations, we don't believe that the right way is to replace the human, but make them more efficient, make them a part of curating and becoming the expert to improve the accuracy. Third, to get maximum insights, correlate the data. There's a lot of insights sitting in databases, mainframe applications, back office applications, social behavior. Connect them and you get better insights. And lastly, in industrial scenarios, it's not just about people monitoring. There's a big diversity of subjects that you have to observe. API-based approaches to develop such applications will not scale, in my opinion. Maybe it won't give you the best accuracy since they developed from scratch. And having a partner such as Matroid, in my opinion, was a great, great thing. In conclusion, I would like to thank some of the team members, the entire Matroid team that was extremely helpful in us engaging and really awakening this industrial IoT sector. And my old colleagues from Oracle, Alex Zuev, Alex Budukov, Ankit, and Chiru, that were extremely helpful in this. So thank you very much, and we have about 5 minutes for time.
Thank you, Supreet. Question over there?
Yeah, can you hear me? I have to bend it down quite a bit. So first, I have a background in industrial IoT, and I appreciate your talk because I agree with pretty much everything you said, and I think it's important context for this room. But I wanted to go back to one of the first things that you mentioned. I also have a background in time series astrophysics, and you talked about multispectral imagery and what it can offer in terms of contextualizing things that you see. You didn't really touch on how that drives the need for scale and what that means from a application development standpoint and also an infrastructure standpoint. So I was wondering if you could comment on that.
Sure. So multispectral, great example would be the SAR imagery. SAR are the satellites that use microwave radiations to do the observations. Because this is a very different area, we don't have a lot of labeled data for that, so supervised learning doesn't work as much. And the question comes, how do you do unsupervised learning for it? And what we did in partnership with Matroid was that the search by example, the collections feature that Reza showed yesterday, that required massive infrastructure of scale to index so that you can select any particular feature of interest and say from SAR imagery. SAR imagery is very different than optical, especially when shadows fall, like other things. So now you can start doing search by example, and that requires indexing at a large scale, categorizing the objects, and that's where the scale factor kicks in for multispectral imagery specifically.
All right, let's thank Supreet one more time. Thank you, Supreet.